All right, chapter 11, vectors. We're going to take a look in section 11.1 at vectors in the plane. So we're going to do a little bit of a setup, and then we're going to do a lot of examples today. So here's our setup. So to describe the velocity of a moving object, we need to specify both its speed and direction. We represent a quantity, such a quantity, graphically as a directed line segment. Directed line segments look like rays. We denote, excuse me. Oh, I was right. It's just typed right on my paper. We denote the directed line segment extending from the initial point P to the terminal point Q by PQ, and it even looks like the symbol from geometry with rays. So PQ with the arrow on top. We refer to the length of PQ. So unlike a ray, it does have a specific length. It does not go infinitely, out, right? We refer to the length of PQ as its magnitude. And we denote that with double lines on either side of the PQ, the arrow notation. And mathematically, we consider all directed line segments with the same magnitude in the same direction as equivalent. regardless of their initial point. And we use the term vector to describe any quantity with both magnitude and direction. Okay, so imagine what this is talking about in terms of the equivalent one is the one I want to draw a picture of. So imagine here's our xy coordinate plane, and we have a vector that looks like this, sitting right there. And I'm going to copy and paste this, at least I say I am. And any vector that's the same direction, the same length, are considered equivalent vectors. Okay, it doesn't matter where they start, it doesn't matter where they're sort of located. The location is not what makes it the vector, it's its length, that's the magnitude, and its direction. So these are equivalent vectors. Okay, so we're gonna do lots of examples. You ready? Lots of them. All right. So the first thing we're gonna look at is we're gonna look at finding a vector. So we're gonna find a vector with initial point A and terminal point B. And our A is the point 1, 1, and B is the point -2, 4. And everything that you want to be true about vectors just is. It works. It's very nice. This happens when we talk about limits. It happens when we work with derivatives until we hit the product rule and the quotient rule, right? Everything that you expect and anticipate works. So when we're looking at the vector AB, vector notation, there's two notations that we're going to be using. One has these kind of arrow brackets on each side. That's the one I'm going to use first, and then I'll show you the other one. And what we're doing is we're just taking the terminal point, which is the coordinates of the terminal point, so -2, and subtracting off the initial point, so -2 minus 1, and then the terminal point's y coordinate, which is 4, minus 1. And of course, we'll simplify this, so I would have what? -3, 3. I'm going to draw a picture in just a second. So this is one notation, is to do it with these kind of bracketing symbols. Another notation, which you do see used in physics a lot, is IJ notation. And we will get to having a K as well, but we're not working in space in this section. It's just two-dimensional, so I's and J's. So instead of writing this, I'll just write the final value. Instead of writing the values inside of these, almost it looks like coordinate pairs is what it kind of looks like, we actually write it as 3I, and there's often a little hat that's put on it like that. Or you will sometimes see it, like when it's typed into something, it's like bold. So I can't do bold on my screen very well, and you can't do bold on your paper very well, so the hats work pretty nice for this. So 3I, and then, plus 3J. Okay. I and J indicate direction, so I is the direction, that's the X direction, right, your horizontal direction. J is your indication of your Y direction, sort of the vertical direction. And in terms of a picture, this didn't ask me to draw a picture, but we can develop that idea pretty easily if we take a look at a grid. And I'm going to actually swap it out for a grid real quick to see if we can make this work better. Okay, so if I plot the points that I'm given for the initial and the terminal points, I'm given the point 1, 1. So that would be here. And I'm given the point -2, 4. A little bit off my grid, but that's okay. And so the directed line segment or vector that we're talking about looks like this, right? And if you take a look at the vector I have at the end, the negative 3, 3, negative 3, 3 would be here, right? And again, if I draw it well, what this vector is, that point that I'm finding, is actually the same vector that would happen if I started at the origin. So my lines aren't perfectly parallel, they should be. But this is the vector's result that I get, right there. It's almost like every time we're finding this, we're resetting the vector to the origin, because the vector can be set anywhere we wish, and they're equivalent. So that's what we end up with, is this resultant vector. Hannah?
So like, I just want to make sure I'm getting this right. So then,
Sure.
like, we plot like the actual points, but then the real vector is coming from the origin.
So it's not that it's the real vector, all right? They're both equivalent vectors. The vector notation resets everything to the origin by default. Like, that's the process that we're following.
Okay.
Yeah. Okay. All right, let's take a look at another one. What we're going to do on this one is we're going to, and I'm going to explain it as we go instead of showing you all kinds of rules and things ahead of time, but we're going to combine vectors. So we're going to add vectors, we're going to subtract vectors, we're going to use constant multipliers times vectors, things like that. And so we're going to go to another screen and take a look at computing some vector arithmetic. So we're going to compute, and there's going to be a lot of them. So I'll list them out as A through whatever I have, I don't know. This is the A plus B. Part B is A minus 2B. Part C is 3A. Part D is the magnitude of 5B minus 2A. I haven't shown you how to find magnitude yet, but I will. And then it asks us to do an illustration and illustrate what letter am I on? I didn't write these on my notes this way. E. Illustrate A plus B, which we would have already found, but we're going to do an illustration for it, a graph, and A minus B. Looks like we're doing a lot of work, but all the work's really quick. Okay, so even though this problem has lots of parts, all the parts are really fast to do. So let me give you A, and a B. So A is 2, 4. Notice this is a vector. The vector A is the vector 2, 4. And B is the vector 3, negative 1. Okay, so again, as promised, everything works the way that you would expect. So on part A, if I'm trying to add the vectors A and B, I just add them component-wise. So I have 2 plus 3. Those are the X or the I components. And then I add the J components, the 4 plus the negative 1. And the result, of course, is 5, 3. Just like you would expect. So what do you think is going to happen on B when I'm supposed to be doing A minus 2B? Yeah, so I take each of the components and do the same thing component-wise, right? So the A component, again, was 2, so it's just 2. And then the B component is 3, so I need to take this to be minus 2 times 3. And then I do the same thing with the J components. So I have the A's J component, which is a 4, minus 2 times B's J component, which is a negative 1. So what will I get for part B? Okay, is everybody good so far? All right, so maybe I should have done B and C in the different order, but C is just 3A. What would I do for just 3A? Yeah, I just take the vector A and multiply each of its components by 3. So 2 times 3 would be 6, and 4 times 3 would be 12. All right, so D is the most interesting one. D is asking me for magnitude, and I haven't shown you how to do the magnitude yet, but let's actually do the part that's inside of the magnitude bars first. So let's actually just find the 5b minus 2a part first. So 5b minus 2a, and then I'll do the magnitude after we're done with that. So for 5b minus 2a, we're going to do it much like we did part B. I'm going to multiply the I component for A by 5, so 5 times 3, minus 2 times the B's component, I's component for B, which is a 3. Did I get that right? I think so. And then I'm going to do the same thing with the J component, so I've got 5 times 4. Oh, I haven't written backwards. Yeah, no, you're right. That's actually what my notes said, and then I looked at it wrong on my screen. Thank you. Okay, and then 5 times, I was about to do it wrong down here too. Right? Yeah, I had them backwards. Okay, so there's a 5. The B's J component, -1, minus 2 times A's J component, which is 4. Okay, do I have them in there right now? Okay. All right, some arithmetic going on here. 5 times 3 is 15 minus 2 times 2, 4. So 15 minus 4 gives me 11. And then we have -5 minus 8. So I have -13. Okay. So I want to give an image about what's happening here so that we can justify what's happening when we find magnitude. So 11, -13, if I started at the origin, I would be going 11 to the right, and I would be going down 13. So I'd have something that looks like this, roughly speaking, right? I mean, there's no scale, and I'm not doing anything like that. I just want an image in my mind. How do I find the length of that? Pythagorean theorem is it. So whatever these lengths are right here and right here, which we know what they are because we've already found them, right? This one is 11 and this one is 13, but in a negative direction. And then we use the Pythagorean theorem. So to find magnitude, it's just an application of the Pythagorean theorem. So if I want the magnitude of 5b minus 2a, all I have to do is take the square root of 11 squared plus -13 squared. So what is 11 squared plus -13 squared? Square root of 290. Does it simplify? I didn't have a calculator when I was playing with the notes on this the other day. Nope. It has factors of 2, 5, and 29. Lots of primes, none of them matching. So 290, square root of 290 would be my magnitude. Any questions on that? Okay, so we still need to do our illustrate ones. I'm going to use the same screen that I'm on and just shrink some stuff. And then I'm going to change it into a grid mode for us to look at it. Okay, so E is to illustrate A plus B. And I know we know what A plus B is. We did it on part A. I mean, I get that. But I want to show you how it looks on a graph and why it justifies that that should be reasonable. So we're going to take our coordinate axis, and we're going to plot the vectors A and B individually. So the vector A is 2, 4. So if I go right 2 and up 4, this would be my vector for A. Is everybody good with that? Okay. My vector for B is 3, -1. So 3, -1 would be over here. And if I draw this one in, it looks like this. Okay, everybody good so far? Okay, so do you remember earlier when we said that all the vectors that are in the same direction and of the same length are equivalent vectors? Remember that? So what we're going to do is instead of starting our new vector at 0, right, like when I do a plus b, I'm going to start it wherever a ended. So if a ends at 2, 4, that's where I'm going to start my vector b. So instead of going right 3 and down 1 from the origin, I'm going to go right 3 and down 1 from here. So I end up with the same vector starting at 2, 4 that I had before. And so it should look like I've almost got, a rectangle here at this point, right? That's not uncommon, or at least a quadrilateral, depending on the angle measures given. This one would be a quadrilateral at least. So I've got 3 sides of it. And the vectors that we get as a summation vector is the vector that connects the beginning point, that is the origin where we started, to the ending point, that is where we end after doing vector b. And if you take a look at what point we're at, what point do we end at here? 5, 3. Look back at part A. What did we find? 5, 3, right? It's the same resultant vector. So this is part, that wasn't right. I get all of it. Part E. Okay, so part F is quite similar, but it's supposed to be subtraction, right? I have this distinct memory of 7th grade math. And I remember the teacher telling us over and over again, there's no such thing as subtraction. There's no such thing as subtraction. And it was just this mantra kind of thing. Because she kept saying it's not really subtraction, it's what? Adding a negative, right? And that's what she was trying to ingrain in us, is that these ideas that they're the same thing. So when we look at A minus B instead of A plus B, we're very much going to think of the minus B as adding a negative. So the A value that I had from before, or the vector I had from before, will be the same. So this is my 4, 2 vector for A. I'm sorry, 2, 4. But instead of my B vector, which I'll draw in real quickly, being down here, it's going to go the exact opposite direction. So instead of going right 3, down 1, it's going to go left 3 and up 1. That's exactly the opposite, 180-degree different direction. So instead of it landing where it was before, it's going to land over here in quadrant 2, like this. And if you can imagine, and this, me drawing the B in itself is not really all that helpful, but that's the vector that I want to sort of shift up to the end of where A ended. So instead of A going right 3 and down 1 from the end of the point A at 2, 4, I'm going to go left 3 and up 1, which is going to put me here. Doesn't look great. Maybe we can do that a little bit better there. And if we didn't do this, in arithmetic form earlier on, like we did on the last one, but if we went back and we component-wise subtracted, we would end up with this value. And the vector that we end up with now is actually, let me draw it in blue, is actually this vector. So we could actually identify what it is too if you wanted to from a graph perspective. It's -1. And it looks like it's 5, right? -1, 5. That's where it's ending. That is the vector too, but that's where it's ending, is -1, 5. So the actual vector here, if we wanted to write it down, is -1, 5. Okay, cool. So remember, there's no such thing as subtraction. All right, so we're going to look at some theorems that vectors have. This is a good review of properties. If you haven't seen some of the properties of algebra in a while, you'll remember some of these anyway, and we'll see if we can remember names for them all. All right, so this is theorem 11.1. And we need a little bit of details at the beginning to make sense of what comes next. So we're doing vectors for any vectors A, B, and C in V2. V2 is just the two space vectors. It's like saying R2 for the real number line. So two spaces for vectors. And scalars. Scalars are just numbers. We're going to use the letters D and E. And these are real numbers. The following properties will hold. So the first one we've actually talked about already a couple of times is that if we do A plus B, right, we can also do it as B plus A. Do you remember what that property is called? It's the commutative property. So I won't write the word property on all of them because they're all going to have the word property after them. But this is commutativity, right? It's being able to commute. So that's the first one. The second one says that if I have A plus B plus C, this will equal A plus B plus C. What's that property called? Associative. And associative is this idea of what we're associating together. That's why the parentheses are grouping them. It's an associative process. And the third one says that if I take the A vector plus the 0 vector, I get back the A vector. And specifically, it's the additive identity. And I do want to use the word additive because we're going to have multiplicative as well. And of course, the values are different. They work a little bit differently. The fourth one is A plus negative A. The A vector plus the negative A vector is the 0 vector. What's that one?
Inverse.
Yeah, it's the inverse property. It's an additive, again, specifically inverse. Five and 6 are different but related. If I have a scalar multiple D times the sum of vectors A and B, I am able to distribute that D through to each individual vector like so. And of course, even in doing so, I told you that the property is the distributive property. And number 6 is very similar. Number 5 has us distributing a scalar through the sum of two vectors. But number 6 has us distributing a vector through the sum of two scalars. So I have scalars, D plus E, times a vector A, and I can distribute the vector A through to each scalar. So dA plus EA. And it's again the distributive. Two more. 7, the coefficient or the scalar 1 times a vector A is just a vector A. This would be the multiplicative identity. And I don't think that it's supposed to be a scalar 1. I think it's supposed to be a vector 1, so I will take that back. It's not written in my notes, right? But I'm certain it is. The point is that we're supposed to be doing vector properties. Yep. So the vector 1 times this vector A would be the vector A. And the last one is if I have the vector 0 times the vector A, I get the 0 vector. And this one would be called the 0 property. I didn't say, I was told you I wasn't going to write this word property. I feel like I have to on this one. I can't just write 0. It looks weird. All right, they're all properties, but that's a 0 property. So we're going to find some more pieces. Let me actually take a look at the directions of the next one with you. And again, we'll define what they're asking us to do as we do it. I think that's helpful for these instead of defining too much in advance. Part A we've done before. So on part A, we're going to find the magnitude. Okay, so that's not anything new. B, however, is a little bit different. B wants us to find a unit vector in the direction of V. And the vector V that we're working with on this problem number 3 is the vector 2i plus 4j. Okay, y'all know how to find magnitude. Let's do that one first. So part A for this is to find the magnitude of V. So what would I get? The square root of what? Yeah, so 4 plus 16, right? 2 squared is 4, 4 squared is 16, so I have the square root of 20. And then we'll simplify that to being what in radical form? 2 radical 5, 2 squared 5. Okay, so part A is not any different. Now, let's for the moment pause and just change up the question a little bit. Let's say you had a vector that was length 3. Okay? It was 3 long. And you wanted to turn it into a vector that was a unit length. It means it's only 1 long. What would you have to do in order to change a vector of length 3 into a vector of length 1? You would divide by the length, right? The length was 3, you would divide by 3. We're going to do the same thing. We're going to take the vector that we have, right, the one that was given, the 2i plus 4j, and we're going to divide it by its length, which is 2 square root of 5. So we're going to take, and this will create our unit vector that's asking us for. We'll call it u. Oftentimes it calls the unit vector u. And we take the components, and I'll write them in ij form because I've worked with that on this problem already. So I have 2, and I divide by 2 square root 5, and this is the I component. And then I have the 4, and I divide by 2 square root of 5, excuse me, and that's the j component. Now, we've really done what the directions asked, but you've done plenty enough math to know you're not going to leave those components in that form, right? For 1, I've got the j component has a 4 on top and a 2 on bottom, so I can definitely reduce that. And for number 2, I have radicals of numbers that are in the denominator. And we don't leave radicals of 5, like this one, in the denominator. We rationalize them. So we're going to do both of those things. So this 2, just like the 4 I mentioned, is going to reduce, and this 4 and 2 will reduce. So then the other thing that I need to do is I need to multiply by square root of 5 on top and bottom. Okay, so the whole point when we rationalize is that it eliminates the radical because the square root of 5 times the square root of 5 would just be 5. So now on top here, I just have the square root of 5 because the 2's canceled. So this is square root of 5 over 5i. And then on the next one, I still have a 2 on top. So it's 2 square root of 5 over 5j. And if you don't like to write the ij notation and you'd rather write it with those triangle kind of brackets, that's totally fine. It doesn't bother me in the slightest. So choose your favorite in terms of notation and go with that. Any questions on that? All right. Next one, we're going to find, directions are going to change slightly, but they're going to be building upon what we just did. We're going to find a vector v with the given magnitude in the direction of u. So we want our new vector that we're calling v to have a magnitude of 5. And the unit vector that we are given is the vector 3, 1. Okay, so pause for a second and talk again about my vector of length 3 that I mentioned earlier. If I wanted my vector of length 3 to be a unit vector, I divide it by 3. Now, what if I want that vector to have length of 5? What would I do? You'd multiply by 5. So we're going to just tack on a step at the end of what we did to find a unit vector. We're going to make a unit vector, and then we're going to multiply it by the length of the vector we actually want it to be. So we'll find our unit vector first. So our unit vector, we need to find, actually let me take one step, let me lower this. We need to find the actual magnitude of the vector u that we were given, and then we'll find our unit vector. So what is the magnitude of u? Yeah, so 3 squared, which is 9, plus 1 squared, so I get square root of 10. So my unit vector, and I'll use this notation this time, is the 3 that I'm given, and I divide by square root of 10. And the 1 that I'm given, and I divide by square root of 10. But I'm not going to leave them in that notation, right? I'm going to multiply by the square root of 10 to rationalize. So this is 3 square root of 10 over 10 and square root of 10 over 10. That's my unit vector. And then the vector I'm looking for, we'll call it our new vector, or you can call it v, because they actually identify it as v in the first part of the problem, will be to take the vector's unit vector, right, the one that I just got, and multiply it now by 5, because I want my length to be 5. So this is 3 square root 10 over 10 and square root 10 over 10. And I'm multiplying by my 5. So what does this give me?
3 root 10 over 2 and root 10 over 2.
Yes. Any questions? Okay, last one. I know you're like, seriously, one more? Yes, one more exactly left. This one actually feels like something we did in the last chapter. So let's see if you can identify. So we're going to find the vector with the given magnitude and angle to the positive x-axis. And I have magnitude of 2 and an angle of pi over 3. So magnitude means that's the length of my vector. The angle tells me the angle it's forming with the positive x-axis. What does it sound like I'm doing? Sounds like polar. So all of the equations that we saw in polar coordinates apply. So x equals r cosine theta. Well, r is the length of my vector, it's 2. And theta is the pi over 3. And y equals r sine theta. So 3 sine of pi over 3. Isn't it pi over 3? Oh, there's that 3. Sorry, thank you. 2 here. Perfect, yes, thank you. All right, so I know you know how to use unit circle, so I'm not going to belabor the point here too much. Cosine of pi over 3 is 1/2, so 2 times 1/2 gives me the number 1 on the first piece. And then on the next one, I have square root 3 over 2. So 2 times square root of 3 over 2 gives me square root 3. And so my vector here ends up being the vector 1 and square root of 3. All right, so let me write the homework up really quick and then we'll be all done. So this is page 759. It's numbers 6, 7, 17, 18, 21, 24, 36, 37, 45, 48, 50, and 51.